So I will speak about Coherent, sheaves, Chern character, and Riemann-Roch-Grothendieck. So this is joint work with Xu from Paris and Zhaoting Wei from Texas University. So here is the organization of the talk. So briefly speaking, I will speak about coherent sheaves. So this is an object that you know well on algebraic manifolds. These are much simpler objects. We will speak actually in general complex manifolds. So the whole point will be to extend to coherent sheaves what is known that we know how to do in the case of holomorphic vector bundles or of algebraic vector bundles on algebraic manifolds. So basically, I will explain the construction of the Chern character for coherent sheaves. I will state the Riemann-Roch-Grothendieck formula in this context, and I will detail the proof in the case of a special case, which is the case of submersion. So basically, then let me briefly explain what I'll do in some detail in the talk. So I give myself X to be a compact manifold. I introduce a d-bar operator Dolbeault, and its square vanishes. So a little generalization is a concept of a holomorphic vector bundle. So you give yourself a vector bundle with antiolomorphic connection nabla E second and with square vanishes. And you know that basically locally antiolomorphic vector bundles are just trivial. So basically by trivialization, you can reduce yourself to the case where nabla E second is just d bar. So what I will talk about is, from a technical point of view, is an extension of that. That is, instead of looking just as one vector bundle, we will look at, in some sense, a Z-graded vector bundle, and it will be equipped with something which is more general than anti-holomorphic connection, than the notion of anti-holomorphic superconnection. So that's still an operator which resembles still the d-bar operator, but basically it has terms of various degrees. A connection has only terms in degree 1 from the differential form point of view, and it preserves the degree of the vector bundle. Anti-holomorphic superconnection will be more general than that. The vector bundle will be Z-graded, and it will contain terms of various degrees in the anti-holomorphic algebra, but still its square will be 0. So the point of this is that actually it will allow us to give a complete description of more general objects than holomorphic vector bundles. These are coherent sheaves. So basically, as I explained, we will construct the Chern character and give an extended index formula that's a Riemann-Roch-Grothendieck formula. So first of all, vector bundles and Chern character. I will start at the very elementary level. I give myself X to be a compact manifold, and I introduce K0 of X. That's the topological K theory. This is generated by, this is a Grothendieck group that generated proper way by the smooth vector bundles on X. So you have this Chern character map, which maps a K group into the even rational cohomology of the manifold, that the Chern character. And this is a ring map. So there is a ring struck on both sides, and Chern character preserves the ring structure. So Chern-Weil theory is like saying that if you give instead a vector bundle with connection, or in that case with unitary connection for simplicity, you can construct Chern character forms. Chern character for E associated with a connection nabla E, and these lie in closed even forms, in the Theorem complex closed even forms, and these forms represent the Chern character in cohomology. So to explain the refinement, I will introduce in the context of coherent sheaves, we will stanch the cohomology of the manifold. I will introduce the so-called Chern cohomology. So you give yourself now X to be a compact, complex manifold. Now, it's well known that the de Rham complex is bigraded by the holomorphic and anti-holomorphic degree. So I will introduce the Chern cohomology of X with coefficients in C. That's a bigraded vector space. And that means that what you do is that you look at PQ forms which are closed. And instead of quotienting, like in de Rham cohomology, by the image of D, you quotient here by the image of D bar D in the proper degree. So basically, if X is scalar, the de Rham cohomology coincides with the Chern cohomology. So Chern in principle is more refined, but in the case of scalar manifolds, and in particular of projective manifolds, de Rham and Chern coincide. In general, Chern is finer than de Rham. So in general, what you can show is that it's still finite dimensional algebra, and which is strictly finer than the de Rham cohomology. So let me introduce H equal. That's just the direct sum of the Chern cohomology groups in degree pp, in equal degree. And because there is a conjugation involution, you can define what is real Chern cohomology in this equal, each equal real Chern. So let me explain how to construct Chern character for vector bundles with values in Chern cohomology. So I give myself X to be again compact complex, and E now, nabla E second, is a holomorphic vector bundle. I give myself GE to be a metric on the vector bundle. And then, as is well known, you can construct the Chern connection, the associated Chern connection, whose curvature RE is of type 1, 1. I wrote the curvature as being the square of the connection, as is classical. So then you can compute the Chern character form, as usual, by taking the trace of the exponential of a suitable normalization of the curvature. So this is still, again, a real closed form. But now what Chern essentially showed in their fundamental paper is that the Chern cohomology class, if you view this closed form and you view it as line is representing of Chern cohomology class, this class does not depend on the metric. So in other words, the class is not only independent of the metric in the de Rham cohomology, it's independent of the metric in Chern cohomology. And so this way, you get a Chern character map, which maps holomorphic vector bundles into Chern cohomology. This map is denoted CHBC of E. One can also compute other characteristic classes in Chern cohomology, like the Toth class, by exactly the same construction. Now, before coming to coherent sheaves, I will slightly generalize the previous construction by moving to holomorphic complexes of vector bundles. So in other words, I give myself EV to be a holomorphic complex of vector bundles. So what does this mean? This means that you give myself a Z-graded holomorphic vector bundle. E0, E1, EM are the components in various degrees. And besides, I have a chain map V, so that V squared equals 0. And this V is also holomorphic. So this is the definition of a holomorphic complex of vector bundles. Now, from this complex, you can construct basically a hypercohomology chain map that is combine the connection nabla E second with a chain map V. You can add these two, and with a proper grading, this map is still such that its square vanishes. In other words, nabla E second square vanishes, V square vanishes, but because of antiolomorphy and taking into account the proper signs, the square of this AE second also vanishes. So then this AE second obviously commutes in some sense with multiplication by holomorphic functions. And so this way you get an OX complex, a complex over the sheaf of holomorphic functions. And because AE second square is equal to 0, I can try to compute its cohomology as a sheaf. You just do the computation locally on a small open set on the manifold X. So let me call H script E. This H script E is a cohomology of this sheaf, E equipped with a differential AE second. Now, what you can very easily show using the Poincaré lemma for a Dolbeault cohomology is that this HE is nothing else than the cohomology of the sheaf of holomorphic sections of E equipped with a chain map V. So in other words, it's a different cohomology, but these two cohomologies are equal. So locally, the cohomology of the sheaf HE, H script E, it's just the cohomology of the complex of holomorphic sections of E equipped with a chain map V. So this HE is an example of a Z-graded coherent sheaf. So in other words, this cohomology of OXEV is the typical example of a more general object that we will introduce later on. That's a coherent sheaf. So let me give again an example of that will be the causal complex. So I give the example of the causal complex just in complex dimension 1 over x equals c. So x equals c and z is the generic coordinate in c. EV in this case will be just the chain map, will just be complex with 2 degrees, E0 and E1, and V, the chain map, is just multiplication by Z. So I again introduce A second, which is V plus D bar. D bar is obviously a holomorphic connection of 2 copies of C. I introduce I to be the embedding of 0 of the point 0 in C. And what you can prove very easily is that HE, which is the cohomology of the complex associated with A second, the sheaf cohomology, is just a direct image of the trivial sheaf C by the embedding I. That's a trivial computation. So let me now define more generally what coherent sheaves are. So by definition, a OX sheaf, so you give yourself F to be a OX sheaf, and you will say that it is coherent if locally you can describe it in the form F equals HE. So in other words, that means that locally you can give yourself a holomorphic complex of vector bundles such that F locally is given by HE. So what is the difference between a coherent sheaf and a holomorphic complex of vector bundles? The difference is that this E here is only local. It is not global. In general, it is not global. So you only assume that F equals HE locally, that this E only exists locally. So an example of a coherent sheaf is exactly if you take X to be a compact complex manifold and you take the direct image of the trivial sheaf, is very easy to show. that this direct image sheaf is coherent using causal complex, but I will not go into that. So in the case where the manifold X is projective, and if F is a coherent sheaf, then you can prove there exists a global EV such that F is equal to HC. So in other words, if F is coherent, basically you can show that there is a globalization of the construction of E. So actually there is no difference between coherent sheaves and holomorphic complex of vector bundles. However, in general, this is not the case. If you give yourself a complex, compact, complex manifold, in general, coherent sheaves do not have, there is not such an EV corresponding to the coherent sheaf. There is a well-known counterexample by Claire-Voisin, and the counterexample is actually very simple. It's a non-projective manifold. It's a generic torus, non-projective, of dimension bigger than 3. If you take the coherent sheaf, just a direct image of a point, you can show that in general, this sheaf does not have, there is not an EV, it doesn't correspond to a holomorphic complex of vector bundles. So let me now explain the question of constructing the Chern character for coherent sheaves. So what we want to construct is a Chern character mapping coherent sheaves into the Bott-Chern cohomology. So if X is projective, if you give yourself a coherent sheaf, we know that there is a global complex E, a whole global complex of holomorphic vector bundles. So then you can construct the Chern character of the complex itself, because these vector bundles are global. And what you can show very easily is that this Chern character does not depend on the choice of E. And so this way, on a projective manifold, you can define the Chern character in Bott-Chern cohomology for coherent sheaves by simply reducing the construction to the case of vector bundles. If X is non-projective, because there is no such a global complex of vector bundles E, which corresponds to F, there is a priori, or there was no such way of constructing the Chern character. And this is a solution to the problem, of this problem that I will present. Of course, there were various stages and people participating in the construction. I won't give all their names. I will simply try to focus on what we have done in the simplest possible case. So I will now introduce a fundamental object introduced by Jonathan Bloch called Anti-Holomorphic Superconnection. So I give myself still X to be a compact complex manifold, and E is a smooth Z-graded vector bundle. And I assume that it is also a free module on the anti-holomorphic exterior algebra. So in the sequel, I will be able to assume it's not too much of a restriction to take E to be actually of the form anti-holomorphic exterior algebra tensored with D, where D is just a classical Z-graded smooth vector bundle. In general, the construction is more general than that. This description of E is non-canonical, but I will forget about this in the remainder of the talk. So basically, you can take E to be the tensor product of the anti-holomorphic exterior algebra tensored with D, which is a Z-graded vector bundle. So what is an anti-holomorphic superconnection? A is second. That's an operator of total degree 1. So E is naturally Z-graded, right? I mean, you have the Z grading where you add the degrees in the forms and in D. So the operator AE second has to be of total degree 1. It increases the degree by 1. It acts on the smooth sections of E. It verifies, like the classical D-bar operator, Leibniz rule with respect to multiplication by smooth anti-holomorphic forms, and its square vanishes. This is a definition of an anti-holomorphic superconnection. So again, you can write, if you wish, you can expand EA second as in degrees, in various degrees, either by looking at the degree in the anti-holomorphic algebra or by the degree in D. So actually, I wrote this A second as V. So V is just a morphism of D, which increases degree by 1. Just V is a matrix. Of course, it's a smooth matrix. Nabla D second is just a connection that preserves the degree. V2 is a 2 form with values in morphisms. It's total degree 1, so it's degree 2 as a form, degree -1 as a morphism, V3, V4, etc. So obviously there is such an expansion. Nabla D second here is not a holomorphic structure. It is not a holomorphic structure on D. Its square in general does not vanishes. The square which vanishes is the square of AE second. So basically you can find a list of compatibilities between these V, Nabla D second, V2, V3, etc., so that the total square vanishes. So let me again, because AE second commutes with multiplication by holomorphic functions, you can introduce the sheath cohomology HE associated with the operator AE second. So let me state the fundamental theorem of Bloch, which in these forms was reproved by Shushen, Wei, and myself. It says that the sheath cohomology of this anti-holomorphic superconnection is a coherent sheath. And the second point, which is fundamental, is that basically all coherent sheaths are obtained this way. So in other words, from such operators, you obtain a coherent sheath, and on the other side, from a coherent sheath, you can rebuild an anti-holomorphic superconnection. Of course, the statement is more precise than that, is formulated as an equivalence of categories. I will not go into details, but the statement says basically during this talk, you can say basically from anti-holomorphic superconnections, I get all the possible coherent sheaths. Let me just outline the principle of the proof. The proof is essentially an extension of the Nuremberg theorem. The Nuremberg theorem says that any holomorphic vector bundle is locally trivial. You can, after a gauge transformation, reduce the Nabla second to being the D bar. That's exactly the same situation here. What we prove is that after a gauge transformation, the notion of gauge transformation has to be qualified. The gauge transformation also involves differential forms, which is not the case in Nuremberg. Locally, after gauge transformation properly understood, you can reduce yourself to the case where A second is just of the form V plus Nabla D second, where locally A D second is just a local holomorphic complex of vector bundles. But this description, again, is only local. So before I explain the construction of the Chern character, I will briefly develop exotic Hodge theory. This I will lose later on. So I give myself X again to be a compact complex manifold. If alpha is a differential form, I wrote it as F1 Fm, wedge Fm. I define an evolution on differential forms at alpha tilde. You just reverse the order and introduce a minus everywhere. So alpha tilde is minus Fm, wedge minus F1. So I introduce the following bilinear pairing or Hermitian pairing between two forms, alpha, beta, in the Theorem complex. I introduce theta of alpha and beta. There is here a scaling parameter. The i's to the n is important. And you take the integral of alpha tilde wedge beta bar. So this is obviously a Hermitian pairing, but it defines a Hermitian form. Hermitian form, it's exactly when you have Hermitian product. That means that when you interchange alpha and beta, you just get the conjugate expression. This is not difficult to prove. So theta is a non-degenerate Hermitian form on the Theorem complex. It is actually of signature infinite. This you can verify for yourself. And so what I claim is that it is possible to develop a Hodge theory based on this Hermitian form. Instead of being based on the Hermitian classical L2 product, it will be based on Hermitian form. So in this context, then, the adjoint of the D-bar operator, of the Dolbeault D-bar operator, with respect to the Hermitian form, is just D. And so, more generally, if you give yourself a Hermitian vector bundle, you have the nabla E second, you can actually construct the proper adjoint of nabla E second with respect to this new pairing of differential forms. And what you find is that the adjoint of nabla E second, the formal adjoint in the operator theoretic sense, is just a Chern adjoint. It is just nabla E prime. So that the curvature, or E, the curvature of a unitary holomorphic vector bundle, is just, in a certain sense, an exotic Hodge Laplacian in which the pairing of forms, the classical L2 pairing, has just been replaced by what I called the intersection pairing. So we're going to use this to construct the Chern corrector form for coherent sheaves. So I give myself again E to be a vector bundle, which is a tensor product of the anti-holomorphic exterior algebra tensored with D, exactly as before. I give myself HD to be a Hermitian metric on the vector bundle D. And I now construct, given a holomorphic superconnection AE second, right? So I take again the operator AE second with this general long sequence of terms. This defines a differential operator, and I take its formal adjoint with respect to exactly the same sort of pairings as before. In other words, I introduce the obvious pairing on the anti-holomorphic exterior algebra, which was defined by an intersection pairing. And then there is a pairing on the vector bundle D coming from the metric. So this way, I can define the adjoint AE prime of AE second. That's literally an adjoint with respect to this Hermitian form. Then I construct, exactly like Chern, the superconnection AE, which is just the sum of AE second A plus AE prime. That's the analog of the Chern connection. Now, let me explain the construction of the Chern character for these coherent sheaves. So this is a theorem that we proved altogether. first theorem, it says I take the Chern character form in the proper sense, where this phi here is a normalization by 2i pi. Don't take it into account. You take the exponential of minus the curvature. The curvature of a superconnection is still a tensor, exactly like in the case of Chern-Weil theory. And you take its supertrace. Supertrace means here just alternate sum of traces in all the possible degrees in the vector bundle D. So this is a form which is real. It's omega equal, that is, there is PP, it's a sum of forms of type PP. And it is closed. And if you look at its Bord-Chern cohomology class, it does not depend on the metric, on the choice of HD. It does not depend. It depends only on AE second. So that's a theorem that's a strict analog of what basically Bott and Chern had proved. But there is more than that. So this is the hardest part of the theorem. This says that this map induces a Chern character from K of X. So what is this K with little point below? This is a K group of coherent sheaves. In exactly in the same way as you can construct the K0 of X, the topological K theory, you can construct the classical Kx with little dot up, which is a K group of holomorphic vector bundles. Now we have a bigger K group, which is a K group of coherent sheaves. And what I'm saying is that the previous Chern character defined via anti-holomorphic superconnections actually defines a Chern character map from the Grothendieck group of coherent sheaves into Bord-Chern cohomology. Okay, so this is somewhat harder. I mean, actually, the computations take place in the so-called derived category. This is an object I've not introduced because of, I mean, many reasons, because otherwise I would never finish my talk, the dBCOH of X. And so basically, I cannot detail the construction. And so now we have a Chern character from the group, Grothendieck group of coherent sheaves with values in Bord-Chern cohomology. So let me now move to Riemann-Roch-Grothendieck. So direct images of coherent sheaves. I give myself X and Y to be compact, complex manifolds. Then there is, let me briefly explain a big theorem by Grauert and Grothendieck, which says the following: if you give yourself F to be a holomorphic map from X into Y, and there is a direct image functor, F shriek, which goes from K dot X into K dot Y. K dot X and K dot Y are the corresponding Grothendieck groups of coherent sheaves. There is a certain functor, which of course verifies all the compatibilities of functors. So this is a big construction, and it does not rely on the projectivity, the algebraicity. This is valid for any compact, complex manifold. So just as a remark, in the case where F is a submersion, let me take the case where F is a submersion and the object you start with is a holomorphic vector bundle. So let me take F to be, say, a proper submersion. Even in this case, if you start from a holomorphic vector bundle, the direct image is not in general a vector bundle. It is just a coherent sheaf. And so the direct image refines on the index of the families of the fiberwise D-bar operator. Okay, so in other words, it's much refined with respect to what the classical smooth families index theorem can give you. It's really the holomorphic structure is captured into this F shriek. So direct image and Chern cohomology. So this is a simple proposition. There is a direct image functor from the Chern cohomology of X into the Chern cohomology of Y. This is a functor of integration along the fiber, and the construction of this functor is actually easy. But its proof relies on the fact that Chern cohomology can also be defined using currents instead of using smooth forms. So why do we need that? Because actually the natural functor F, this one here with a star below, there is integration along the fiber which maps currents into currents, that the dual map to the pullback map. The pullback map maps the RAM complex into the RAM complex. So dually, you have a direct image map which maps currents into currents. And since Chern cohomology is the same, whether you use forms or currents, this is not an entirely trivial statement. You can ultimately define this direct image functor from Chern cohomology of X into Chern cohomology of Y.
Yeah.
Yes, there is a question? No? Okay. So this is a functor. That is, it's compatible with composition of maps. So let me now state the theorem of Riemann-Roch-Grothendieck, which the three of us proved. And then, I mean, you can guess what the statement is, because the advantage of Riemann-Roch-Grothendieck theorems is that whatever category it takes place into, the statement is always the same. So in other words, if you take F to lie in the Grothendieck group of coherent sheaves on X, then you have the obvious natural equality in the Chern cohomology of Y. So all this left-hand side, for instance, makes sense. This is taught Chern of Ty. Ty is a vector bundle. So it has a taught class in Chern cohomology. I explained the construction at the beginning. CHBC of the direct image, it's also well defined. It's a coherent sheaf. And the right-hand side is just integration along the fiber of the corresponding Todd and Chern classes. So, as usual, I would say as usual, because this was the way that Grothendieck himself explained how to prove Riemann-Roch-Grothendieck. Once you know functoriality, you can reduce the proof to the case of immersion, or better say embeddings, and submersion. You only need to prove the proof in these two cases. And once you have functoriality, you deduce general Riemann-Roch, because any map F from X to Y can be factored trivially as a product of an embedding and a submersion. So I will explain in more detail the proof in the case of submersions, but let me give, first of all, a simple application of the result we proved. So I give X to be a compact complex manifold, and I consider IX to be the embedding of the point in the manifold. That's a special case of an embedding. Okay, as a consequence of our theorem, we get, in some sense, a fairly obvious statement that I'm sure you would have guessed, that the Chern character of the direct image by the embedding Ix of the trivial sheaf is just given by the Dirac mass at X. Okay, so this statement actually was, in some sense, could not be proved before, because as I explained before, by Clairvoisin argument, there was no holomorphic complex of vector bundles corresponding to this direct image sheaf, and so you had no theory in which such a theorem could be true. Now it is simply a trivial consequence of the theorem I stated before. So I will now explain the proof in the case of submersions. Actually, because of the factorization of maps I explained before, actually we can take a very simple submersion, that the submersion from X cross S to S, we can actually suppose that the fibration in some sense is trivial. And we will take F, the coherent sheaf. I directly take it to be associated to his E. He is actually the couple of E and anti-holomorphic superconnection. So in other words, I immediately start in the case when my coherent sheaf is given by such a anti-holomorphic superconnection. So again, I take E script to be the space of smooth sections of E equipped with the anti-holomorphic superconnection AE second. Now, remember that the vector bundle E is a module over the anti-holomorphic exterior algebra of M. But in some sense, since the form on the base S, okay, so we have the base S here, S, okay, maybe I will change my pencil to make it, write something. I hope that this will work. Yeah, well, maybe it doesn't work, okay. Yeah, okay, maybe. I have the base S here. Oh no, okay, so it doesn't matter. Okay, so you have the base S, and what I'm saying is that if you have differential forms on the base, anti-holomorphic forms, they lift to anti-holomorphic forms on M, so that actually this space, C infinity of M and E, is a module on the anti-holomorphic forms on the base. This is trivial. And so that you can view AE second, instead of viewing it as a differential operator acting on the total space of the manifold M, you view it as a differential operator but acting on smooth sections of an infinite dimensional vector bundle. Okay, maybe this will, oh no, I'm not able to write this, sorry. I'm trying to find where the pencil. Yeah, maybe it's this one. Yeah, no, it doesn't work. So AE second, because you can view this space as a module on anti-holomorphic forms on the base, you can interpret the operator AE second and being an anti-holomorphic superconnection on an infinite dimensional vector bundle, which is the direct image of his script. It is just, this is a tautology. It is not a mathematical statement. It's just a way, two different ways of seeing the same thing. So in particular, for instance, what I'm saying is that if E is just the trivial vector bundle, that just means that you can view D bar M, the total operator D bar, as a sum of the D bar along the fiber and of, in some sense, the D bar on the base. This is like writing the total operator D bar M as an anti-holomorphic superconnection in the sense of block. So a dilemma. Why do we have a dilemma here? Is that on one hand, we know that the direct image, it is a coherent sheaf. So in other words, the cohomology of this complex over S, locally over S, it's a coherent sheaf on S. But on the other hand, the object that we used, this infinite dimensional superconnection, is infinite dimensional. So it is not accessible to the treatment I outlined before using block superconnections, because these ones are finite dimensional. So we cannot combine the two a priori. So Bloch's theory does not apply to this infinite dimensional object. So severing the Gordian knot. So we also know, on the other hand, that infinite dimensional Chern veil theory exists. So we know it exists because it has been applied repeatedly in the context of the family's index theorem. So what you do actually to solve this problem, you give yourself a couple of metrics, GTX, GE. GTX is a metric on the relative tangent bundle, on the vertical tangent bundle. GE is a proper metric on the block object. And what I claim is that by adapting the known constructions of infinite dimensional Chern veil theory, we can obtain closed superconnection forms, which are called CH of P star E G on the base S. So these are obtained using, in some sense, the full Hodge-Dolbeaus theory along the fiber, combined, of course, with Bloch's theory. If the direct image is locally free, that is, if the cohomology does not jump from fiber to fiber, it's relatively easy to show that these infinite dimensional Chern classes coincide with the Chern character of the direct image. However, when HP star E is not locally free, this a priori is a hard statement. But using spectral truncation, the above result still holds in general. Okay, I won't explain that. That means that the infinite dimensional construction of Chern character forms still computes the Chern character of the coherent sheaf, which is a direct image. Now we're ready to start trying to use more analytic methods, use local index and Riemann-Roch-Grothendieck. So using local index means that we are going now to scale the metric, the fiber metric, replacing the metric GTX by GTX divided by T. So what I'm claiming is that if the Kähler form of the vertical metric, okay, I gave myself a metric along the fiber, GTX. If the Kähler form is d bar d closed, then you can prove that our Chern character forms converge as t tend to 0, and we can prove our Riemann-Roch-Grothendieck theorem in the sense that these forms, a cohomology class doesn't change, we compute the limit, and by computation of the limit, we get the Riemann-Roch-Grothendieck theorem for submersions. However, this requires the vertical form, the vertical metric, to have a Kähler form which is d bar d closed, which is not true in general. So the general case is obtained by hypoelliptic deformation. So in other words, the Hodge theory that we used along the fiber X, the classical Hodge theory in its family's version, is not enough to give us the theorem. We have to go further. So let me go back to the intersection duality I defined at the beginning. So I give myself omega to be a real 1-1 form. Now you can assume, just as we are in the case of one single manifold, forget about the family's case. Omega is a real 1-1 form. I had introduced before this Hermitian pairing between forms on X with alpha tilde and beta bar. Now, it's very easy to show that if you give yourself a 1-1 real form, multiplication by I omega is defined as self-adjoint, is theta self-adjoint. So I introduce a new Hermitian form, which consists in combining the pairing theta with a theta here, the intersection pairing, with the exponential of the Kähler form. The exponential is here taken in the exterior algebra. So this is still a Hermitian pairing. Now, if you take the adjoint of the d-bar operator, the classical adjoint, it is not equal to d. The adjoint of d-bar, before it was d, now it is d minus d I omega. So you find that the corresponding sort of holomorphic Laplacian in this context, the anti-commutator of d bar star, is equal to minus d bar d I omega. And this anti-holomorphic Laplacian is precisely the obstruction to the proof of our Riemann-Roch-Grothendieck theorem in the case of submersions. So we have to do something now which is a bit unusual. I will still explain it in the case of one single fiber. So I introduce X script, which is a total space of the tangent bundle. Its fiber is Tx hat. And what we shall do is replace the manifold X by the total space of its tangent bundle, by bigger space, twice the dimension. Then we basically are going to introduce the so-called causal complex of the fiber. Okay, so let me try to explain this in words. On this total space of the tangent bundle, you have the canonical section Y of the vertical tangent bundle. This vertical tangent bundle and the natural tangent bundle are isomorphic. So this means that what we will do is replace the Dolbeault operator d bar x. We replace the Dolbeault operator d bar x on the base manifold by the total Dolbeault on X script, to which we had the causal map IY scaled by B square. So this operator, its square still vanishes, and it acts on forms of the total space of X script. Its square still vanishes, so it is still in some sense a block-like or d-bar-like. It's a hypercohomology operator. So I finally introduce a vertical metric. So we have in some sense two metrics now, a metric on the base X and a vertical metric on the fiber Tx. We are going to combine these two. We introduce generalized metrics again in a different direction. So basically, we are on the total space of a manifold X script, the total space of the tangent bundle. And we are going to combine two dualities. The first duality is the intersection duality I defined at the beginning on the manifold X, on the base X. Just the intersection duality in which I introduce this little exponential minus I omega. This is, in some sense, a very degenerate duality. But in the fiber direction, I introduce the Hermitian duality. And I combine the two. So in other words, on the base, you have the non-classical duality. In the fiber, you have Hermitian duality. So why do you do something like this? I will not have time too much to explain what happens when you do this. By doing this, you get a new Laplacian LB. Remember, there is a parameter B here, maybe you forgot about it, that scales the causal chain map. It scales the contraction. And this new Laplacian on the total space of the tangent bundle, it is not an elliptic operator. It is not a classical Laplacian. It is actually a hypoelliptic operator. It is essentially the sum of a harmonic oscillator along the fiber and a vector field, which is essentially the geodesic floor. This operator is hypoelliptic on the total space of the tangent bundle. I wrote it maybe in local coordinates LB. You still have, here is the harmonic oscillator in the direction of the fiber. This is the geodesic flow. It differentiates in the base direction, but the intensity is given by y, by this y coordinate, real coordinate in the fiber. And you still have our friend or our enemy, d bar d of omega. So we have a new Hodge Laplacian and a new Hodge theory. So what are we going to do with this? First of all, the fundamental fact is that this theory, when B tends to 0, deforms the classical Hodge Laplacian. This I don't have time to explain. This is a bit hard. There is a collapsing phenomenon which makes that when B tends to 0, the new Laplacian collapses to the Hodge Laplacian on the base. So how is this going to end the proof of our Riemann-Roch-Grothendieck theorem? Well, I mean, by plugging in this construction I gave in the case of one single fiber in the families context, what we get is actually, remember, we have to understand what is the Bord-Chern cohomology classes of certain forms that we constructed using infinite dimensional superconnections. By this hypoelliptic deformation, we get new forms. But these new forms, CHB, they still are equal to the original one in the Bord-Chern cohomology. This is hard. This is not easy. You have passed from one representative to another one. The Hodge theory is different, but still the Bord-Chern cohomology class has not changed. So we can use this hypoelliptic fiberwise Hodge theory instead of the original one. Well, I mean, I told you that d bar d of omega was our enemy. If d bar d of omega, if the Kähler form of the fiber is not d bar d closed, we can still not take the proper limit as the parameter t tends to 0. It still doesn't work. But now we're going to use to exploit the full strength of the hypoelliptic construction. In the duality I gave before, this extremely degenerate duality, I explained that you could introduce the exponential of I omega, the exponential of the form. But nothing forces the form omega to be non-degenerate. Actually, in this duality, we will now make the form omega depend on the vertical coordinate. There are fundamental reasons for that, fundamental geometric reasons that I cannot explain. So you replace in the construction omega by y square omega. You scale the Kähler form of the base by y square. This scaling in classical Kähler geometry is impossible. You cannot Kähler forms which are degenerate. And this one is completely degenerate when y is equal to 0. But however, when you do that, from the point of view of the Hodge theory on the total space of the tangent bundle, not much has happened. You still get a nice Laplacian. You can still prove that the Chern character forms you construct are good. And then finally, you finally take the asymptotics when t tends to 0, and then the asymptotic works. The reason why it works is very simple. You have simply disconnected the metric from the manifold. When you have a Kähler manifold or complex manifold, complex Hermitian manifold, the metric and the manifold are tied to each other. What we have done is progressively detach the metric from the manifold while still working with a proper Chern veil theory, so that once they are far enough from each other, then the asymptotics or whatever analysis becomes much easier, actually very easy. Okay, so this way you get Riemann-Roch force immersion, Grothendieck force immersions, and you prove the Riemann-Roch Grothendieck. So here are just a few references. There is first a reference to Etier and Hirzebruch, because they had raised a long time ago the question of how to represent Chern character of coherent sheaves. Then there was a book by myself in 2013. I mean, absolutely not, I mean, dealing with a special case, but the case, I mean, not block object, not coherent sheaves. Then there is the fundamental paper by Jonathan Bloch. And then there is our John paper with Susan Zouting-Wei. Thank you very much.
Yeah, thanks a lot for the nice talk. So have you any question now?
I have a question.
Yes, please.
Hey, Jean-Michel, so I had one question about, you talk about the K-theory of coherent sheaves and the Chern character to the Bott-Chern cohomology.
Yes.
Is it known whether this map is an rational isomorphism or the reals?
No. I mean, no. This, I mean, very little is known about this, about the map itself. Yes. So it is just, no. The rationality result and so on, no. This we don't know at all.
Okay.
I mean, the construction, I would say even the construction, there is such a distance between the coherent sheaf you start with and the block superconnection which is associated. Is constructed by using repeatedly Poincaré lemma locally. There is a lot of homological algebra, which is involved in the construction of the Chern character. So that we certainly do not have any time to understand any rationality property of the Chern character. Absolutely nothing.
Okay, thanks. And I have a second brief question, which is, the local index theorem for complex manifolds. Can it now be proved by going to the tangent bundle and using the hyperelliptic operators?
Yes.
That's what
So
you're saying.
one of the points of this, let me just explain this as simplest case as possible. You take the non-Kähler complex manifold. So Etier and Singer had proved the Riemann-Roch Hirzebruch formula in this case by using the Dirac, the index theorem for Dirac operators. But in this case, what you do is that you start from the d bar plus d bar star and you deform the symbol to a smooth symbol. By doing this, you do not change the index, but you destroy the holomorphic structure. The point, the context in which I work is the context in which if I do this, if I deform myself in the smooth category, I lose the Bott-Chern cohomology information that I'm trying to compute. I'm going back to the smooth Etier-Singer families index theorem. So from a certain point of view, one can say that what I am doing is proving the Riemann-Roch Hirzebruch theorem by not deforming the bar operator. I just stick the bar operator, but I allow myself to do many nasty things to the bar star. Okay? I do not move the bar. The reason is obvious. I do not want to destroy the holomorphic structure. However, I destroy whatever concept there is of a metric.
Yeah. Well, thank you very much. It's a very beautiful result. Thanks.
Yes. To answer maybe the first question you gave, I mean, I probably was misunderstood because there is a rationality in the Chern cohomology, and the Chern character, when computer understood properly, is rational.
Right.
That is, there is rational Chern cohomology, and our Chern character takes its values there.
Okay.
That's actually a consequence of a result of a student of de Mailly, which is mentioned in our paper. So if there is rationality at this level, there is rational Chern cohomology, and our Chern characters takes its value in rational Chern cohomology.
Okay. Yeah, thanks very much for a lovely talk. I really enjoyed it.
Yeah, so have you other question now?
Can I ask for a question?
Yeah, please.
Okay. When we work on a general complex manifold, and we have a formula on cohomology of holomorphic vector bundles, is there a general strategy or possibility to generalize the holomorphic vector bundle version of this formula to coherent sheaf version?
Sorry, so I missed your question. So you're asking, your holomorphic vector bundle, of course, defines a coherent sheaf. That's less general, yes?
Yes, I mean, if we have a formula on cohomology of holomorphic vector bundles, is there a possibility or general strategy to generalize this formula from the holomorphic case to the cohomology sheaf case?
Yes, of course, yes. So exactly, I mean, with these objects like A second, in exactly the same way as you compute the cohomology of a vector bundle using the Dolbeault complex, you can use the AE second to compute now global cohomology, okay? So this AE second can be globalized, yes? So exactly when you take direct image by, say, by submersions, that's exactly what you do. You look at the global cohomology of the fiber. Yes, absolutely.
Okay.
The AE second allow you local objects, but they are also global, exactly as a D-bar operator itself. You exactly work with this from a cohomological point of view, exactly as you do with the D-bar operator.
Okay, maybe we have to check your papers. Okay,
yes,
thank you.
And Riemann, yes, and so basically, yes, our formula, if you just specialize the formula Riemann-Roch to the case with the base is a point, you just get an index formula for this operator. Yes, you get the Euler characteristic exactly in the same way. You have cohomology groups and you have exactly, yes.
Okay, thank you. Thank you. Very nice answer.
Yeah. Okay, more question now? Yeah, perhaps I have a question. So, yes, what's the rough idea? Why omega become omega equal y square time omega?
Yes. Okay. So there is a first philosophical question first, that all the, I mean, you know, in Riemann geometry, complex geometry, there are many quantities like scalar curvature, Ricci tensor, and so on, which are naturally averages. They are just averages. Scalar curvature, you take the curvature tensor and you make the sum. Sum means integration. Yes. So scalar curvature is even worse. So basically, when you look at a quantity which is an integral, it's sometimes better, if you want to understand this quantity, to work on the integrand than working on the integral. Yes? So the reason why we have to move to a bigger coordinate space is that the scaling parameters are different. These new parameters have a scaling of their own. This extra scaling is destroyed when you work on the base manifold. When you use a Kähler form, you're forced to really use it as it is. You're in a bigger space, you can start sort of viewing as averaged. So from a technical point of view, The fact is that the asymptotics when the t parameter tends to 0, I've not explained what the t is that the coordinates y also enter in the game. They have playing, they can be scaled themselves. They scale. And it is this scale that you exploit. While you work with omega, you have the coordinate y is not there. You're forced to work with omega. I can work with y squared omega. So let me just again explain analytically what's the reason. When I work with omega, just with omega, the operator along the fiber I get is a harmonic oscillator. Is minus Laplacian with respect to the fiber metric plus y squared. Y squared computed with respect to the base metric. When I modify omega to y squared omega, I still get the Laplacian along the fiber, but my y squared is changed into y4. So you see that y4 is still a good, from a certain point of view, it's a good operator because y4 grows at infinity. So the operator, I mean, it still has discrete spectrum. It is still a good sort of Holmes Laplacian. But by having y4, when you have the t parameter in front of it, the coordinate y scales can be scaled in the proper way. It turns out that the weight 2 is in general the wrong weight. So let me give a final explanation. Y squared and d bar d omega are just cousins. They come together. If I have y squared, I have d bar d omega. And d bar d omega is a cause of my index theoretic troubles. Right? They are connected to each other. I cannot have one without having the other. D bar d of omega is the cause of my trouble. If I scale d bar d of omega by y squared, you know, you dream, or it's a nightmare maybe. If you scale it, you discover that when t tends to 0, the difficulty disappears. It's just a little check. Just replace d bar d, you know, make a dream. D bar d of omega, scale it by y squared, you find the index theoretic difficulty disappears. And so this is what you try to do. I mean, we are plumbers, yes? I mean, there is a basic conceptual explanation I won't give in terms of path integrals, I won't give here. But there are many reasons to do that.
Yeah, yes, thank you, yeah. So, have you more questions now? If it is not the case, then let's set the speaker again. So,
Thank you.
So,
Thank you.
yeah.